Hello, everybody. Hi. Thanks for coming out tonight. I know it's a little jam-packed in here, but Burchard was booked, and both of the rooms were booked tomorrow night. So it was this room or nothing, so I figured we'd prefer this room. But yeah, so first off, thank you to SITTV. They're going to be recording this as well. If we can get the link before Friday for the test, they'll send that link to me, and I'll email it out to all of you guys. You can just review this video for extra studying. But there's no guarantees that it'll be processed and ready in time. But I know they always do their best. Should be done by tomorrow-ish. So you guys will have plenty of time to rewatch it and study. But anyway, if you guys don't know where you are right now, this is the SigEp MA221 Test 2 review. My name is Jake Shozer. That's my name. That's my email address. If we could just quiet down a little bit. I know we had a nice long week, got a nice big test ahead of us. But this test is going to be covering these topics right here. So we have undetermined coefficients, variation of parameters. We'll have some Cauchy-Euler, some definition of Laplace transform, and then some solving with Laplace transform. In most of the past semesters, this has been the exact breakdown of the 5 questions on the test. They play around with the order of these a little bit, but most of the time it's going to be these 5 questions. Last semester they changed it up a little bit, and instead of giving you a definition of Laplace transform, they gave you a part A and part B of doing just the inverse Laplace transform, and then they jumped back to solving a full problem with transforms for that 5th question. But again, if you fill out this form right here, I also posted the link for that in the GroupMe. Fill that out, your name, email address, and I'll send out an email with these review notes as well as all the past tests that I have. And I'm pretty sure this exam, I have every test from the previous like 6 or 7 semesters. So you guys will have a lot of material to study from, and you'll notice that it's almost the exact same format for all of them. Does anyone have any questions before I start? Yes. Springs are not on it. Springs are not on the test. They never are. Springs are never on the, none of the modeling problems are ever on the test. So out of the topics that are up here, out of these topics that we have, which one or couple are the worst we know absolutely nothing about? Wow. Okay. Cool. 2. Okay. Cool. So, like normal, I'll be doing a little bit of teaching for each one, give you some like important things to know, and then we'll jump in, we'll do an example problem for each one of these, and then you'll have dozens more example problems with those old tests that you can go for. Are we ready to get started? Okay. Before we do, everyone, nice deep breath. Let it out. I know we got a lot of finals. This is a stressful time right now. But right now, we're going to do some Diffie-Q. It's going to be a very fun 2 hours, and we're going to feel great for our test on Friday. So the first thing we're going to start off with is our undetermined coefficients. So, you know, you ended test 1 with solving for your homogeneous problems, right? Where you were given a differential equation, and on the right side of that was always a 0. Well, now starting on test 2, you're going to have some functions on that right side. And in order to find your solution for whatever on that right side of your differential equation, you have to find your particular solution. And there's 2 ways we can do that, either with undetermined coefficients or variation of parameters. Undetermined coefficients is normally the easier method if we're allowed to use it. We're only allowed to use it in certain circumstances depending upon what that f of x is, whatever the thing on the right side is. So there's 3 different cases that we can have for that f of x. The first case is if f of x is a polynomial. And just to give some context, this would be in a type of problem where you're given like y double prime plus 3y prime plus 4y is equal to some function of x on the right side. And that f of x is what we're looking at right now for these f of x's. So if f of x is a polynomial, so x squared plus 2x plus 3, or x cubed plus 3, it's some form of a polynomial, then your answer is going to be in this form. Your answer is going to take the form of your y particular is equal to ax squared plus bx plus c. And the important thing to remember for this is that it won't always be ax squared plus bx plus c. You're going to just use whatever the highest power in your f of x is going to be the highest power that you start with for your answer. So we want to look at highest power of f of x. So what that means is if my f of x has an x cubed in it, then this has to start off with ax cubed and then work your way down by 1 power of x each time. So it would be ax cubed plus bx squared plus cx plus d. And that would be the form of your answer that you use. So that's one possibility. Now I'm going to try and use different colors to help us differentiate, but if you can't see these other markers, let me know and I'll just keep using the black. So with our second option, if f of x is a sinusoid, and what all that means is it's either a sine or a cosine. Is the green good? No. I'll try purple. Purple better in the back? So our next option is if our f of x is a sinusoid. All that means is it's got either sines or cosines in it. Those are just all generalized as a sinusoid. So if I have something that, my f of x over here is 3 cosine of x, then my answer is going to be a cosine of x plus b sine of x. You have to include both of these even if you only have one. The other thing to note, if our f of x is equal to, say, 3 cosine of 2x, then our answer, we have to keep that 2x here. So our answer would be a cosine of 2x plus b sine of 2x. Yes?
What happens if it's cosine squared x? Then we get to use trig rules?
If it's cosine squared, then you can either use trig rules to try to get it to be not squared and something simpler, or variation of parameters. Because the good thing about variation of parameters is it always works. There's none of these conditions thing. It will always work. It's just a lot of times more difficult because you have to take integrals. Yeah. Going back how far? My name is Jake Shozer. For the purple. So if f of x is a sinusoid, we have all of this. A sinusoid just means that our f of x is either a cosine or sine, even if we only have one of those. So even if our f of x is just something like 3 cosine of 2x, our particular solution has to have both cosine and sine. And whatever we have inside these parentheses, we have to keep inside the parentheses for our answer. Yeah. if it was 3x times cosine of something. So with these, I'll explain that after I do the third situation. Yeah. Yes. Whatever the highest power of your polynomial is, that f of x, is the highest power that we have here. So if we have an x to the 74th, then we'll have ax to the 74th plus bx to the 73rd plus a lot of other terms that they won't give you that many. Okay, so then the last term, we have another possibility, and hopefully blue works well. The last thing that we could have is if f of x is an exponential. And all that means, so this is an e to the x term. This is sine or cosine. So if f of x is an exponential, meaning we have e to some power of x, or e to the x, or it could be e to the 2x, e to the 5x, just e to an x, then we know our answer. This one's nice and easy. We have, it's just a e to the x. And just like with our sinusoids, if we have our f of x is e to the 2x, we have to maintain that e to the 2x in our answer. So this would be a e to the 2x. So if we have f of x is equal to e to the, I'll use 3x here, then I know that my particular has to be a e to the 3x as well. So now, what are these all used for? As I was saying, we look at the problem that we're given, and if we have some function on the right side, we have some f of x, that's where we take these into account. If we look at that f of x, and it's either a polynomial, a sinusoid, or an exponential, we have our form of our answer right there, we're done. But what if I have something like x squared plus 3 plus cosine of 2x? The really cool thing is I can just separate those out into two different problems. I can solve the problem as if it only had the polynomial, get my answer, and then I can solve the problem as if it only had my sinusoid, get the answer, and then I just add those two answers together at the end. And the first question of your test is going to be asking you to do exactly that. Where the right side of your f of x is going to be it's going to have multiple terms, and it's going to ask you to solve for the answer, the particular solution for each term independently. And then the fourth part of the question will say, find the general solution. You literally just add them all together. That has been the same exact format on every test that I have going back to when I took this class in spring 2016. So it's a good bet that that's going to be what the first question looks like. Yes?
So if you have like cosine x plus like x, right, you just do find out a cosine x or b sine x, find that, and you find bx plus c sine x.
Well, yeah, like the ax plus b, yes. You can find two particular solutions, one for each f of x, and then you just add them together at the end. Now, the other thing that I'll mention, and this goes back to the question that we had before, is it gets a little bit more iffy, but if I had something like x times cosine of x, then I can write out my particular solution for my x term, write out the particular solution for that cosine term, and multiply these together to get a nice, much longer particular solution, and use that as my answer that I carry through the undetermined coefficients. It gets a little bit more tricky if we have that. Most of the time, if we have multiple things multiplied by each other, then we're going to use variation of parameters. If we have multiple terms that are added together, then we can do undetermined coefficients. Does that answer the question you had before? Okay. Yes?
Can you think of a case where, so my professor, it was the particular solution of it was e to the 3x, but he said something about a magic factor, and whereas a e to 3x, he just added an x. Do you know, like,
Yes, we'll get into that when we're doing the problem. The reason that happened is because that guess matched something in his homogeneous solution. So, question? Yeah. Sometimes. So the question was, are they going to tell you which of these methods we have to use? I've seen on some tests they'll say, solve this using undetermined coefficients, solve this using variation of parameters. In other semesters they say, solve this problem, and it's up to you to decide which one. But if you can use undetermined coefficients, it is almost always the easier way because you don't have to take any integrals. And when you're doing variation of parameters, you do have to do integrals, which can sometimes mean integration by parts, U substitution, other things that we don't like to hear. So I'm now going to jump into the first problem. And most of the problems that I use from tonight, I'm just going to do the most recent tests, so spring 2019. I don't have the full solutions to these, so if you see me make a mistake, let me know. But we'll see how it goes. So we have y double prime plus 2y prime is equal to 9e to the negative 3x plus 8x. So this was the first question, and it just said, consider the differential equation that. Part A said, find the general solution of the corresponding homogeneous equation. So it basically just said, find the homogeneous solution. So in any particular solution, anytime we have to find a general solution, anytime we're using either of those first two methods, first step is always to find the homogeneous. We have to do that first in order to move on to the others. So I know for my homogeneous, this is going back to what you did on the first test. I can set up my auxiliary equation. We have an m squared plus 2m is equal to 0. I get m, and m plus 2 is equal to 0. I get m equals 0, and m is equal to negative 2. And if that's what I have for my two m's, then I know that my homogeneous solution, so y sub h, is going to be c1 e to the 0x plus c2 e to the negative 2x. I'm just going to simplify that. So we have yh is equal to c1 plus c2 e to the negative 2x. So that is my homogeneous solution. Now I move into my particular solution. And this is the type of problem where they break it up, so we'll solve it the same way that they do, because part B of the problem says find a particular solution of the equation, and it just has this written. So it ignores the plus 8x. It says find the particular solution to this equation with just the 9e to the negative 3x. So that's the only thing we're going to be looking at for this particular, for part B of this problem. So part B, it says we have y double prime plus 2y prime is equal to 9e to the negative 3x. So I look at this and say, okay, am I going to use undetermined coefficients or variation of parameters? And you guys should probably understand that we haven't done variation of parameters yet, so it's probably not that option. So we're going to use undetermined coefficients. Now, the question is, which of those three does it fit? Is this a polynomial, is it a sinusoid, or an exponential? Well, we see that it's an e to a power, so we know it's an exponential, which tells me that my answer, y particular, is going to be ae to the negative 3x. We have to maintain that negative 3 because we have a negative 3 up there. So the next thing that I have to do before I move forward is I have to double check to make sure that this doesn't match any of the terms in my homogeneous solution. So what does that mean? I need to look to my homogeneous solution and see if I have any term that is constant times e to the negative 3x. Because if I do, then I have linearly dependent terms, going back to the whole Wronskian thing. And what that would mean that I would have to modify that using that magic modifier that you mentioned. But I look here and I look here and I have no term that matches. So I'm good to go. I can keep moving forward with this. So I know the reason why I called this my answer is because this is the answer to the differential equation. The only thing that I don't know is my coefficient. You might say that it's undetermined. You get it? Undetermined. So if this is an answer to the problem, then I should be able to plug it into the problem that they gave me, and the left side should equal the right side, right? That's how we're used to dealing with equations. Just because we got some fancy derivatives in here doesn't mean that that changes. So I'm saying that this is an answer. I should be able to plug it into what they gave me, and the left side should equal the right side. So in order to plug this in, first I have to take the first and second derivatives, and then I can plug those into the left side, set it equal to the right side, and it should be true. So let's take those derivatives. I know my first derivative is going to be negative 3a e to the negative 3x. And my second derivative is going to be positive 9a e to the negative 3x. So now I can take both of these, plug them into what I was given, and set up that equation. So we have y double prime is 9a e to the negative 3x plus 2 times y prime. So it's going to be minus 6a e to the negative 3x. And that's going to equal 9e to the negative 3x. So now we can see that all of our terms have this e to the 3x, or e to the negative 3x. So we're going to be looking at all of our terms that have that e to the negative 3x and just looking at the coefficients on the left side, the coefficients on the right side, and setting up an equation so we can solve for that variable. So I look at the coefficients in front of my e to the negative 3x terms, and I have 9a minus 6a is equal to 9. So then I can solve this equation. We have 3a is equal to 9, which means a is equal to 3. And I now found that coefficient. I can bring it back up here into my answer. And I have y particular is 3e to the negative 3x for this equation right here. Now the next part of the problem says to solve the particular for that plus 8x. So we have the same thing on the left side, y double prime plus 2y, but now it's just going to be equal to 8x. And we're going to be doing the same steps for this. First thing we ask ourselves, undetermined coefficients or variation of parameters? It's going to be undetermined coefficients. Now, is it a polynomial, sinusoid, or exponential? This, even though there's only one term, it still has an x to some power. That means it's a polynomial. So my y particular is going to be a times whatever the highest power of x is in my polynomial. And this is just x to the 1. So I'm going to have ax, and then I have to include every power of x below that. So x to the first, x to the 0, which is just 1. So our particular solution is ax plus b. Just like we did here, we have our particular solution. Let's take our derivatives so that way we can plug it in. But before we do that, I almost forgot this step, we have to check here to make sure that nothing matches our homogeneous solution. And when you check that, what do you see? We have this plus b, which is just a constant, and in our homogeneous solution, we have a term that's just a constant. So when we encounter that, when we have something in our homogeneous that matches our particular, it kind of sounds a little bit weird. I don't know the full proof behind it, but we just multiply this particular solution by x. The whole thing. So now, instead of ax plus b, it's going to be ax squared plus bx. And now we're going to use, we have to check again to make sure that nothing matches. Nothing matches. We're good to go. Now I'm going to be using this to carry through the problem.
How does ax plus b look similar to the homogeneous?
Because we had, so the question was, how does ax plus b look similar to the homogeneous? we're not looking at the whole thing. We have to check each term. And this term of just the plus b is just plus a constant. And here in my homogeneous, I have C1, which is just a constant. Yes. Yes. So if we had something in here that still matched, because you'll have some times where you still have something matching, then you're just going to multiply this by x again. And you keep multiplying it by x until nothing matches. Yes. No. For any of these methods up here, if you have something that matches, you just multiply by x. When we get to our Cauchy-Euler problems in a little bit, that will change. But for all of these problems, you just multiply by x. Yeah.
If you multiply by x and it still matches, you multiply by x.
Yes. Yep. Okay. So now we have this, and now we're going to take our first derivative, take our second derivative. You can see we're going to do the same exact steps in the same exact order as we did in the purple. So now y particular is, take the derivative of this. It's going to be 2ax plus b. That's y prime. Y double prime is just going to be 2a. I can now take these, plug it into my equation that I'm given. So I have y double prime, which is 2a, plus 2 times y prime. So this is going to be plus 4ax plus 2b. And this is going to be equal to 8x. So now, in this problem, I only had one kind of term. Everything was an e to the negative 3x. But now I have two terms. I have constants, and I have things that are multiplied by x. So first, I'm going to look at all my terms that have an x. And I look on the left side, and I see I have a 4a. And then on the right side, I see I have an 8. So we have 4a is equal to 8. And then I'm going to look at all my constant terms. On the left side, I have a 2. So I already used this, and I already used that. On the left side, I have a 2a plus 2b. On the right side, I have no constant terms, so I just set it equal to 0. And just like I did here, now I have to solve that system of equations. So the first one's nice and easy. We just divide by 4. We get a is equal to 2. I can plug that into my second equation, and I get 4 plus 2b is equal to 0, which means b is equal to negative 2. Now that I've found out those coefficients, I can plug them back in up here. So I get y particular is equal to 2x squared minus 2x. So I now have my homogeneous solution. I have my particular solution for the 9e to the negative 3x. I have my particular solution for the 8x term. And then, so this is the exact problem will be, this will be part A, part B, part C, and then part D just says write the general solution. And the general solution is your homogeneous plus your particular. So our general solution is just going to be our homogeneous, which is C1 plus C2 e to the negative 2x, plus our particular solution, which we have two things that we have to combine. So we have plus 3e to the negative 3x plus 2x squared minus 2x. It's a little sloppily written, but that right there is the answer to this differential equation. Yes? If the right side is just a constant, that fits the polynomial term. Yes? If your f of x is just a constant, then your y particular is just going to be a, right? Because it's just ax to the 0. I doubt they'll give you something like that because then all your derivative terms are just 0. And that's going back to like your equilibrium solutions from test 1, I think. Yeah. They probably won't give you a constant on the right side. Any other questions on this? Yeah. Write the general solution. Cool. Yes. Laplace transforms. There's a very weird integral, then they'll give that to you, but you'd still be expected to do like U substitution, stuff like that. But they'll give you integrals if you need it and Laplace transforms. And you can see them at the end of the test that I'll send back, what they normally give out. Okay. So the next type of problem that we have is variation of parameters. You're only allowed to use undetermined coefficients when it fits one of those three conditions. So you're allowed to use undetermined coefficients more specifically when you have constant coefficients and your f of x fits one of those three formats. So constant coefficients meaning like notice how we have 1 times y double prime plus 2 times y prime. If I had a x times y double prime, that is now a variable coefficient. It's not a constant coefficient, so I can't use undetermined coefficients. So very specifically, it's when you have a constant coefficient equation and your f of x fits one of those three conditions. Now, if you have something that's like a first order where you only have y to the single prime, theoretically, yeah, you should still be able to use undetermined coefficients, but you're not going to have anything that's to the first power on this test other than maybe Laplace question. So the next thing that we got is variation of parameters. This is our other way of finding that particular solution, meaning when we have something on the right side. And this one, the great thing about variation of parameters, it always works. There's no conditions, no matter what your coefficients are. It could be constant or variable coefficients. It could be ln of x. It could be 1 over t squared. No matter what your f of x is, no matter what, variation of parameters works. But a lot of times this could be harder because notice how these terms are given as u1 prime and u2 prime, which means in order to find our u1 and u2 for our answer, we have to take the integral. And sometimes those integrals can be a little bit tricky. But what's going on here? The answer for our variation of parameters is always, our particular solution is u1 times y1 plus u2 times y2. Now, where does this y1 and y2 come from? The y1 and y2 come from your homogeneous solution, which is why you need to solve for the homogeneous before you can do this. Because your homogeneous solution is in the form of c1 times y1 plus c2 times y2. So whatever isn't your constant is your y1. Whatever's not your constant here is your y2. So you take those terms and they go into your answer, but they also go into the formulas for how we find our u1 and our u2. So u1 prime is negative y2 times f of x over a times the Wronskian of x, the Wronskian. Now, f of x is just that thing that's on the right side. A is everything in front of your y double prime. 98% of the time, A is just going to be 1, so you're going to forget about it. And then you're going to get to a Cauchy-Euler problem where in front of your y double prime, you have an x squared. You're going to forget to divide by that x squared. You're going to get something that is impossible to take the integral of. You're going to sit there very confused, have no idea what to do, and probably start crying because you forgot that that a goes in the denominator. It's so bad that even in my own notes, I didn't write the a in the denominator because you very rarely ever use it. Most of the time, the only thing that you're going to use it for is in a Cauchy-Euler problem, but don't forget that it needs to be there because I've already had people tell me that on the homeworks they've forgotten it and they couldn't solve it. Whatever is in front of your y double prime term is that a, and you have to divide by it in both of these y1 and y2 prime terms, or u1 and u2 prime terms. And then our Wronskian of x, it's the same thing that we're doing on test 1. It's this matrix with y1, y1 prime, y2, y2 prime, which evaluates to that. So we notice the only difference between these two terms is for our u1 prime term, we have a negative y2, and for our u2 prime, we have a positive y1. It's the only thing difference between these two. So once we know all of our information, it becomes a plug and chug. Most of the time, one of these integrals is going to work out to something very nice. Things are going to cancel out, and you'll have like the integral of a constant or the integral of x. Very easy. The other one is most of the time going to be a little bit more complicated. Sometimes it's going to involve u substitution. So be ready for that. But this is pretty much everything you need to know for variation of parameters. So now we're going to jump into a problem where we have to do all this stuff. Like this. What did that say? 12x e to the 2x. Cool. So the next problem that we got, we have y double prime minus 4y prime plus 4y is equal to 12x e to the 2x. Now my first question is, can we use undetermined coefficients on this if we wanted to? Yes. Because if we have forms that fit our undetermined coefficients, either added or multiplied by each other, so here we have a polynomial term, and here we have an exponential, we can do that. This question, though, specifically said, use the method of variation of parameters to solve this. And if it specifies that you have to use variation of parameters and you don't, then they might give you, like, if it's a 20-point question, you might get like 5 points, if even that. Question? Yeah, you would, well, so you would actually have to do it all in one. You wouldn't be able to separate it out. You would have to write out your answer format for 12x, then write out your answer format for e to the 2x, multiply those together, and then take the derivatives and plug them in. You couldn't solve one, then solve the other, and multiply them. you have to multiply them from the beginning. So this one doesn't give us a choice. We have to do variation of parameters. So what is our first step? Homogeneous, thank you. So we always have to start with our homogeneous. Should be experts at this by now. Why homogeneous is going, oh no, I skipped. Our auxiliary equation is m squared minus 4m plus 4 is equal to 0. I know that this turns into m minus 2 squared is equal to 0. So this means that I have m equals 2, and I have repeated roots. So since I have repeated roots, I know that y homogeneous is going to be c1 e to the 2x plus c2 times x e to the 2x.
If you put the x in the first with the c1, it doesn't change, does it?
No, it's the same thing. If you want to put the x in this term or the x in that term, it's the same thing. The only difference would be if the problem gave you initial values, your c1 and c2 would be swapped from what I had, but it's the same answer.
Can you put the y particulars if we were to do just like what it would look like?
I don't want to because it gets pretty complex, and I recommend that if you have something that's multiplied to do variation of parameters, because I'm not even sure of exactly how all the coefficients combine and what kind of overlaps with the homogeneous you have to discount. So I'm not even sure of it. If you have things multiplied, I recommend doing variation, because that's most of the time what they're going to be looking for anyway. So we have that, which means so because we now have this homogeneous, I know that my y1 term is everything multiplied by my c1, which is this e to the 2x, and my y2 is x e to the 2x. So now I can jump over here and write down my equations. Jump back to. I know that u1 prime is equal to negative y2 times f of x over a times the Wronskian. And u2 prime is equal to positive y1 times f of x over a times the Wronskian. So the good thing is my y1 and my y2, I know those already. My f of x is just this 12x e to the 2x. My a is everything in front of the y double prime. So right here, it's just 1. The only thing that I have to calculate before I can plug stuff in is my Wronskian. So let's do that. So I'll do it right over here. The Wronskian is going to be equal to the matrix of y1, which is e to the 2x, y2, which is x e to the 2x, the derivative of y1, which is 2 e to the 2x, and the derivative of y2, which we have to do the chain rule for it, or the product rule for it. So this is going to be e to the 2x plus x e to the 2x. Now I'm going to do that times that, top left times bottom right, minus bottom left times top right. So I'm going to have e to the 4x plus, oh, this should be a 2. Yeah. So it's the first times the derivative of second. Yeah, this derivative should be e to the 2x plus 2x e to the 2x. I forgot that too. Thank you. But anyway, when we multiply these two, it's going to be e to the 2x times e to the 2x, which is e to the 4x, plus 2x e to the 4x, minus, we multiply these, which is 2x e to the 4x. Notice how those two go away, and we're left with our Wronskian is equal to e to the 4x. If when you're taking your Wronskian, things don't cancel out and you get something that has like 3 different terms in it, you probably messed up somewhere. Very rarely are you going to have ever more than 1 term in your Wronskian. Because if you did, it would make this step very not fun. So now that we have our Wronskian, we have our y's, we have a, we have f of x, we can start plugging everything in. So we'll do our u1 prime first. So my negative y2 is going to be negative e to the 2x. F of x. Oh, yeah, y2, my bad. I did y1. So we have negative x e to the 2x times our f of x. So times 12x e to the 2x divided by 1 for our a times e to the 4x. It looks really complicated right now, but things are going to cancel out very nicely. Because in the numerator, we have an e to the 2x times an e to the 2x. In the denominator, we have an e to the 4x. All of those divide out. And what we're left with is, in the numerator, it's just going to be a negative 12x squared, which is something we love to see, but that also probably means that the next one won't be as pleasant. Actually, it's going to be more pleasant. You guys got lucky with this one. So we now have positive y1, which is e to the 2x, times 12x e to the 2x over 1 times e to the 4x. All of your e terms cancel out, and you're just left with 12x. Beautiful. So now the last step that we have to do, because I don't care what u1 prime is, I want to find what u1 is. So I need to take the integral of this. So we have the integral of negative 12x squared dx. When I take the integral, I raise the power by 1. I divide by that new power. So it's going to be 12 divided by 3, so it's negative 4x cubed. And then when I take the integral of just 12x dx, it's just going to be 6x squared. So I have now, I'll write it right here, we have u1 is equal to negative 4x cubed. And we have u2 is equal to positive 6x squared. So now I look up to my answer. I need u1, y1, u2, y2. I now have all those pieces, so I can write out my particular solution. Y particular is equal to u1, which is negative 4x cubed, times y1, which is e to the 2x, plus u2, 6x squared, times y2, which is x e to the 2x. So I'm going to make this 6x cubed e to the 2x. But notice how we now have both of these terms are an x cubed e to the 2x. So I can combine these together. And we get our y particular is going to be equal to 2x cubed e to the 2x. And now most of these problems, they're going to be asking you to find the general solution. Question?
I know you said that a is everything in front of the y, but where is it talking about?
In the problem that they give you. So this problem right here, a is everything in front of your y double prime.
Oh, okay.
Say, question. Correct. This is positive. So the last thing is, a lot of times these problems will end with write the general solution. And we know that the general solution is our homogeneous plus our particular. I'm not going to write it out right now, but know that our whole general solution, we would write out the full thing, would be c1 e to the 2x plus c2x e to the 2x plus 2x cubed e to the 2x. And that is our final answer for this problem. Does everyone understand how to solve for your particular solution no matter what you're given? Cool. Question. No, not on the test. They might have asked some weird stuff on the homeworks, but they won't give it on the test. What? The general solution is always homogeneous plus particular. Yeah. Question. The initial conditions. I didn't notice it on last semester's test. Normally they'll throw initial conditions on one problem on this test. Just because like, okay, this problem you showed me you know how to do it. I know you know how to do it for all the others. I'm not going to waste time. Cool. Oh, we got Cauchy-Euler. Standard form. No, it's beta ln of x. Perfect. We quieted down right on cue. So the next type of problem we got is our Cauchy-Euler. Now, all of the problems that we've dealt with up to this point with undetermined coefficients, variation of parameters, all of those had constant coefficients. Those are, we've only dealt with, we've never had anything other than a constant in front of our y double prime or our y prime. This is the problem where that's going to change. For Cauchy-Euler, it has to obey this specific format of in front of a double prime, you have an x squared. In front of a single prime, you have x to the first. In front of a y to the 0 prime, you have x to the 0 or just 1. And this a, b, and c just represents constants. So they could be numbers, they could be 1, whatever. But the standard form, we know that we have to use Cauchy-Euler if it's in this format of x squared y double prime plus xy prime plus cy is equal to, this could be 0, this could be some function of x. When we're solving for our homogeneous with Cauchy-Euler, we're going to be using an auxiliary equation. It's very similar, but a little bit different than what we're used to. This time, it's still going to be the a m squared, but now it's going to be b minus a times m plus c equals 0. So the only difference is for this middle term, you have to do b minus a, where usually you're used to just doing am squared plus bm plus c. We have to remember to change that up in the middle. Now, when we solve for our m terms, just like we do normally, we can have 3 different cases, 3 different conditions for those m's. If we get m1 and m2 don't equal each other and they're real numbers, so you get m1 is 3, m2 is 5, then our homogeneous solution takes this form, where we have c1 times x to the m1 plus c2 x to the m2. Notice we're not dealing with e's anymore, e's to some power. We're dealing with x to the power of m. Case number 2 is if we get m1 and m2 are equal to each other, so we get m is equal to 3, and that's our only root, then normally we'd just multiply by x, but now this ln of x comes into play. So our homogeneous would be c1 x to the m plus c2 times ln of x times x to the m. And then if we get imaginary, normally that's where our sines and cosines came into play. This is definitely the weirdest because if we say that our m is equal to alpha plus or minus beta I, right, we're dealing with imaginary numbers, then our homogeneous is x to the alpha times c1 cosine of beta times ln of x plus c2 sine of beta times ln of x. Gets pretty funky. And if a problem asks us to find the particular solution, so if the problem gives us some f of x, which method do I have to use to find that particular solution? I got 2 choices, undetermined coefficients or variation of parameters. I have to use variation of parameters because I have non-constant coefficients with that x and the x squared, so undetermined coefficients does not work. I have to use variation of parameters to find the particular solution for a Cauchy-Euler. Is everyone ready to jump into a problem? Sweet. So this is the problem that we're starting with. The only thing that the test said was find the general solution to the following to the initial value problem. And it gave us this. So how do I know that I have to use Cauchy-Euler for this? Because I see this x squared and a y double prime, x, y single prime. I have to use Cauchy-Euler. So first step is find the homogeneous solution. So I need my auxiliary equation. So I know that I have a 1 here, and then a 5 and a 4. So my equation is going to be 1m squared plus 5 minus 1 times m plus 4 is equal to 0. So we have m squared plus 4m plus 4 is equal to 0. I know that this just becomes m plus 2 squared is equal to 0, which means that m is equal to negative 2. And which of the three cases am I in right now? The second one, right? Because I got repeated roots, so I know that I have to use that purple case that we have. So my homogeneous solution is going to be C1 x to the m, which is negative 2, plus C2 times ln of x times x to the negative 2. So this right here is my homogeneous solution. If the problem didn't give me initial values, I'd be done. It's beautiful. Because I know that I have no particular solution for this problem, because it tells me that the right side is 0, f of x is 0, there is no particular. So I have this, but it gave me those initial values, so I need to solve for C1 and C2. So let's bring this over here. We have YH is equal to C1 times x to the negative 2 plus C2 ln of x, x to the negative 2. And then I know my second condition has the derivative, so I'm just going to take that derivative right now, get it over with before I start plugging stuff in. So my YH prime is going to be equal to, this first term is nice and easy, it's just negative 2 C1 x to the negative 3. This term's not going to be so fun. We have plus, I'm going to take the derivative of the first, so it's going to be C2 times the derivative of ln of x is that 1 over x or is it ln of x plus x? It's 1 over x. Okay, cool. So the derivative of that is just going to be 1 over x times x to the negative 2 plus the first, which is C2 ln of x times the derivative of that, which is negative 2x to the negative third. I'm going to simplify this a little bit. We have y homogeneous prime is negative 2 times C1 x to the negative third plus C2, this is just x to the negative 3, minus 2 x to the negative, or 2C2 x to the negative 3 ln of x. Now I can start applying those initial conditions. And for those initial conditions, I'll do the first one first. So what this is saying is when x is equal to 1, y is equal to 5. So I have 5 is equal to C1 times 1 to the negative 2 plus C2 ln of 1 times 1 to the negative 2. Now I know 1 to any power is just 1, so that's C1 plus C2 times, what is the ln of 1? 0. Music to my ears, because I know that that whole term is going to cancel out, and all I'm left with is C1 is equal to 5. So I can take that over here, along with my second initial condition, and I say that negative 3 is equal to negative 2 times 5 times 1 to the negative third plus C2 times 1 to the negative third minus 2 times C2 times 1 to the negative third times ln of 1. I know this whole last term is going to cancel out because I have an ln of 1. And I'm left with negative 3 is equal to negative 10 plus C2. I add 10 to the other side. I get 7 is equal to C2. I have my C1 and C2. I can plug them in to this homogeneous right here. So C1 is positive 5. C2 is positive 7. And this is my final answer. And this is my general solution because I have no particular. So that right there is the answer. Can we get those 20 points on the test? Let's get these 20 points. The Cauchy-Euler problem, the only time it gets really funky is if they throw on either that case 3 where you have the imaginary, or I have seen them throw on variation of parameters where they'll give you an f of x here. Then it gets pretty funky. But if they give you something just like this with initial values, let's get those 20 points. Yes? I'm not going to do an example, but there is an example on one of the old tests that you can look at. You're welcome. It was on my test, so spring 2016. Yeah. Spring 2016 is the one that has the imaginary. I did get it wrong, though. I was close. Listen, I forgot the formula. I like half derived it myself on the test. It was baffling to me. I just put the ln of x in the wrong spot. Nope. So for definition of Laplace transforms, we got that out of the way. Definition of Laplace transforms. Like I said, they didn't have a question on this on last spring's test, but it was on like the previous 3 or 4 exams before that. So we're going to go over it just to be safe. This is all that it is. So the way that we take the Laplace transform of some function of t is we do the integral from 0 to infinity of e to the negative st times that f of t dt. And then the result that we get, it will have no t's left. It'll only have s's, and then we are now in the magical world of Laplace. Those Laplace tables that you have, all of those are just using this equation to transform from your t to your s. They just already did it for you, so you don't have to do it for every single problem. If they ask a problem like this, this is going to be, if they specifically say use the definition of Laplace transform, that's the only time you'll ever have to use this equation. Every other time you're doing a transform or an inverse transform, you're just going to look at the tables because they'll provide you the tables. So we're just going to do one problem right now, really quick. The problem that I'm doing, this is from my test in spring 2016 just because they didn't have one on last semester's test. But we'll run through it nice and quick, and hopefully we'll get that down and we can move on to the more fun Laplace stuff. Yeah. So I'll give you like the 2 seconds of what Laplace is actually doing. If you have no clue, don't feel bad. I only fully understood it last spring when I took control systems. So any mechanical engineers that have to take control systems, it actually like opened up my eyes. Like the Laplace domain is so powerful. The idea of what the Laplace transform does is, and you'll see this a lot more when we're solving with Laplace transforms. We're using this in differential equations because a differential equation in the Laplace domain, normally you have to, like y prime, you take the derivative of it to get the y prime form. In the Laplace domain, to take the derivative of something, you multiply it by s. So when you're dealing with t's, if I want to take the derivative, so like dy dt, I just do, like I take the derivative of that function, right? And sometimes that function's really complex and not fun to deal with. So taking the derivative can be complicated. But if I transform this into the Laplace domain with s's, and I want to find my y prime, I want to find the derivative of whatever function I'm dealing with, it's just s times y of s. And that's where, when we're doing our solving with Laplace transforms, when you have a y double prime, it's s squared times y of s, because you're taking the second derivative, you're multiplying it by s twice.
Are they going to give us the equations for your Laplace?
Yes. Yes. They'll give you the equations for like y double prime is equal to this in Laplace, stuff like that. But this is like the quick 2 seconds of why Laplace is so cool. Any mechies that take control systems, you'll learn a lot more in that class, which I think it's so much cooler. So if we have this as our problem, a problem like this would just say, use the definition of Laplace transform to take the Laplace transform of this piecewise function. And it'll give you this. So we have function e to the 5t between 0 and pi, and we have 2 at t greater than or equal to pi. And now I need to somehow apply this equation to this piecewise function. Well, this equation says I need to take the integral from 0 to infinity. I don't have one function that I can take the integral of from 0 to infinity. But I know that if I take the integral of something from 0 to t1, and then from t1 to infinity, that's the same thing as the integral from 0 to infinity. So what all of that is saying is I can break this up into two integrals as long as the first integral lower bound is 0 and the last integral upper bound is infinity, then I still satisfy this condition of 0 to infinity. So they would just say, use the definition of Laplace transform to take the Laplace transform of this. And this happens to be a piecewise function. So let's do that. So we know that we're going to be doing, let's slide this up a little bit. We're going to be doing the Laplace transform of f of t is equal to the integral from 0 to pi of e to the negative st times e to the 5t dt plus the integral from pi to infinity of 2 or of e to the negative st times 2. And since we have 0 to pi plus pi to infinity, we're satisfying the 0 to infinity integral. But this way we can break it up to account for our two different piecewise functions. So I'm going to be taking the integrals of each of these ones independently. And then when I'm done, I just add them together, and I get the total Laplace transform. Now, for test 3, you'll be able to take the transform of this without using this method. You'll learn a different way to take the transform of piecewise functions. But trust me, you'll wish it was this way, because those get fun. But anyway, we look at this first term, where we have the integral, let me write that bigger, the integral from 0 to pi of e to the negative st times e to the 5t dt. Now, I want to combine these a little bit to make it better, because I know if I'm multiplying two things that have the same base, I can just add the exponents. So this really just becomes e to the 5 minus s, and my 5s look like s's, 5 minus s t. Right? Because if I add these together, it's just going to be negative st plus 5t, factor out a t. We're left with 5 minus s times t in that exponent. And the cool thing about this is, you might be looking at this like, I have 2 letters in this. How do I take the integral? I don't like this. Notice that we're taking the integral with respect to t, which means s is a constant. This whole thing in the parentheses, we can pretend that that's just one constant. It's just one number. So if I want to take the integral of this, I know that what's the integral of e to some power t? Well, it's just e to that some power t, but then you have to divide by whatever that power is. So I know that the integral of this is just going to be e to the 5 minus s t divided by 5 minus s. And I'm evaluating this from 0 to pi. So all that I'm doing is I'm going to be plugging in pi for t, and then I plug in 0 for t, and figure out what this answer is. So I plug in pi for t, and I get e to the 5 minus s times pi divided by 5 minus s minus, this is just going to be e to the 0 over 5 minus s. Right? Because when I put in that 0, the whole exponent's just going to go to 0. I know that e to the 0 is 1, so this whole thing can be simplified, and I'll write it down here. The whole thing can just become e to the 5 minus s times pi minus 1 over 5 minus s. Cool. Everyone follow along for this? So all that we're doing is just taking the integral with respect to t, plugging in our upper and lower bounds, evaluating it, and we're left with this. Except this is only half of our final answer. I've only done this left integral. I still need to do the right side. The good thing is the right side's a little bit easier. Question? Okay, no problem. So now let's do the right side. And the right side, we have the integral from pi to infinity. I'm just going to pull that constant 2 out in front. We have e to the negative st times dt. So I can just take the integral of this. Again, s is a constant. So I have 2 times e to the negative s times t over negative s. And I'm evaluating that from pi to infinity. Plugging in these values for t, I have 2 times negative e to the negative s times infinity over s minus a negative e to the negative s times pi over s. Well, if I have s times infinity, that's going to be a really, really, really big number. And if it's a e to the negative infinity, then I know that this is really just 1 over e to the infinity, which means this whole first term is going to go to 0, because I have a really big number as a negative exponent. So all that this term leaves me with is the 2 is still out in front, so I have 2e to the negative s times pi divided by s. And then my final answer for the full Laplace transform of this, I'm just going to add those two parts together. And I get the Laplace transform of my f of t is going to be equal to e to the 5 minus s all minus 1 over 5 minus s plus 2e to the negative s times pi over s. And that is your final answer. Yes. I left something somewhere. I forgot the pi. Thank you. Right there. Any questions on definition of Laplace transform? Because if we have a constant in front, right? So that 5 minus s is a constant. So if I was doing the integral of e to the 3t, this would be e to the 3t divided by 3. Just instead of a 3, we have 5 minus s. This is spring 2016, question 4. They did, it was questions on just inverse Laplace transform. There was like a part A and part B, and you only had to do inverse transform. And then part D was the whole thing, solving the full problem. Yeah, all of that, because you need inverse Laplace to solve with Laplace. So I guess last semester they just decided to break it out into its own problem, but you have to use it for solving. Say that one more time. Yes, we'll give you the Laplace transform. You know how when we're plotting stuff, we can use Cartesian with x's and y's, and we can also do polar with r's and betas. We can represent the same things using different coordinate systems. That's essentially what's going on. It's a whole different domain. Like, things behave differently, derivatives are just algebraic, and that's why it's good, because we can manipulate these algebraically. Yeah, it's weird, but it's cool. It's a whole different world. Imagine the world with pulse. Now you have pulse. Yeah, the definition of Laplace to go. One of the rates on the board.
excited as that box. But it cuts out so much like that.
Last problem now. Last problem of the night. It's going to be a nice fun one. We're going to be solving this using Laplace transforms. Now this problem will say something exactly like that. It'll say find the solution to this problem using Laplace transforms. Let me see this. Now this is the one time where you don't have to start with your homogeneous. Because your Laplace transforms, when you solve it with Laplace, it takes every step into account at once. You find your homogeneous solution, you account for your particular solutions, you account for your initial conditions, everything you do it all at once, which is nice. Are we ready for this? Okay. So you see up there, I wrote the general steps that we have to do. The first thing says we have to take the Laplace transform of the equation we're given. So I'm given this whole thing. I'm going to take the Laplace transform of the whole thing. So, I look at this left side. What's the Laplace transform of my y prime? Now, the good thing is they give you this on that Laplace transform table, so you don't have to worry about memorizing it too much. But the Laplace transform of a y prime, remember how I said taking the derivative is the same thing as multiplying by s? Well, y prime is just s times capital Y of s, but then we have to account for an initial condition. So we have to account for that minus y0. So this whole term is the Laplace transform of y prime. Now the Laplace transform, yes, that's an s. Then the Laplace transform of my y term is just, since it's just a y, I'm going to be doing minus just capital Y of s. The transform of y is just capital Y. But in this Laplace domain. So this right here represents the transform of this left side. Now I need to find what's the transform of my right side. 5t e to the 2t. I know that's going to be a little bit more annoying, so I'm lazy. I'm going to save that for later. I'm just going to write this as the Laplace transform of 5t times e to the 2 t. Knowing that I'm going to have to take that transform later, I'm just going to wait as long as possible. Let me do some other stuff first. So the second step, so I did step 1. I took the Laplace transform of what I'm given. Step 2 says get y of s alone by itself on the left side. So what do I have to do to make that happen? Well, I know what my y initial is, right? I'm given that initial condition, so I can just plug in that 0 right here, which means I just got rid of that. So this is nice. This entire term is gone. And on this left side, I'm left with s times y of s minus y of s is equal to all that stuff on the right side. So what I can do is I can factor out a capital Y of s and say that this is times s, so we have capital Y of s is equal to s minus 1, and that's, or sorry, capital Y of s times s minus 1 is equal to the Laplace transform of this right side. 5t e to the 2t. And then I can just divide over this s minus 1. And I have what my capital Y of s is equal to, is this. Now the next step says rearrange the right side so you can take the inverse Laplace of it. Right now this does not show up anywhere on that inverse Laplace table. So the first thing I have to do is now I actually have to take the Laplace transform of what I'm given. So I've put it off as long as I can, but now I have y of s is equal to something. I got to take the transform so I can manipulate this right side. So we need to take the Laplace transform of 5t e to the 2t. Now if you really wanted to, you could take this f of t, plug it into that equation we just used, the integral e to, or 0 to infinity, e to the negative st times that. You could do that, you'd get the right answer, but you don't have to. For this, we can now go to our transform tables to figure out the answer. So I look at my transform tables, and I'm going to look at that left column for something that looks like this format. So let me I'll write down 3 or 4 of the things that are on the table, just so we can see what our options are to pick from. So we have f of t, and then over here is going to be my Laplace transform, so my capital F of s. So if I have 1, the transform of that is 1 over s. If I have t to some power n, it's going to be n factorial over s to the n plus 1 power. 5e to the at, I have 1 over s minus a. And if I have e to the at times f of t, it is just the Laplace transform of f s minus a. So all of these are copied down exactly from the Laplace transform table. If you want to see exactly what you'll be given, you can look to it's not on every test that I'll be sending out, but on some of the tests I'll be sending out, you'll see the exact table that they'll give you at the back. So you'll know exactly what they'll have. So, and there'll be a lot more other than this. There's like 10 or so on there. I just wrote down a couple that pertain to this problem. So we can now look and see which f of t does this most closely resemble. Well, this isn't just a constant. It's not just a t to some power. It's not just e to some exponent. I think it looks like this one, where it's e to some exponent times another function, right? Because we have e to that 2t times 5t. So we now need to figure out what that means. This is exactly what it gives you on the table. If you don't understand what that means, then the table's worthless to you. But what this is saying is we take the Laplace transform, but instead of it being a function of s, it's now a function of s minus a. So everywhere we see an s, instead we plug in s minus a. So what does that mean? Well, we have 5t e to the 2t. What is my a value? 2 because I have e to the 2t. So I know that a is going to be equal to 2. And what this is saying is to take the Laplace transform, I just take the Laplace transform of f like I normally would, but then everywhere I see an s, plug in s minus a. So let's try that. I'm now just going to take the Laplace transform of 5t. So the cool thing about constants, you can pull them out in front with Laplace. And now I just have the transform of t. So it's t to the first power, and t to the first power is going to be 1 factorial over s to the 1 plus 1, or s squared. So the transform of just this is going to be 5 times 1 over s squared. But in order to account for this e to the 2t, I need to turn all of my s's into s minus a. So what the whole transform is really going to be is 5 times 1 over s minus a squared. And a, we know, is 2. So what this turns into, putting that 5 in the numerator, we have 5 over s minus 2 squared. And that right there is the transform of 5t e to the 2t. Make sense? If anybody sees me mess up at any point, let me know, because I don't have the solutions for these. I'm doing these for the first time right now. But everything so far should be correct. Everything's worked out pretty well. So now I did this whole thing so I can take this and plug it in for my transform right here. So now let's rewrite that. We have capital Y of s is equal to, I have 5, and this s minus 2 squared, I'm just going to throw it into the denominator over here. Because that complex fraction just puts it in the denominator. So we have s minus 2 squared times s minus 1. So now I have capital Y of s is equal to this whole thing. And now remember, looking at our steps up there, we're still in the rearrange the right side so you can take the inverse Laplace of it. I know I didn't write out the full Laplace transform table, but this does not look anything like anything that's on that table. So what do? Give up. The symbol lab is a good option. On the test, you don't have that choice. So we give up, we accept however many points we've got so far, and we give the rest of our time to other problems that we have a chance of getting right. But what do we actually do? Is that an idea or a question? What do we do? Yes. So when I do it's going to be 5 over s minus 2 squared divided by s minus 1 over 1. And this becomes outsides over insides. So it's 5 over that. So I've left you with suspense. Is this a question? Question. What do we got? Because this y is a function. Y is a function, so to take the transform of a function, I do s times capital Y of s. We're over here, this is just t, where t is just a variable, so that I can just use my transform. Okay. So I've left you all in suspense for a long time now. What do we actually do? Partial fraction decomposition. Yeah, that's what I love, enthusiasm. So, what do we do for partial fraction decomposition? The whole idea of partial fraction decomposition is I'm going to break this out into multiple different terms, each that has a much simpler denominator than the one that we have right now. And ideally, each of those much simpler terms, I can then, with that, take the inverse Laplace transform and finally move on to that last step. So how does it work? Well, we have to look at, the denominators are going to tell me how I break this up. So I know I want something that's going to be equivalent to this. I don't want to change the value at all. I just want to reorganize it and rearrange it. So the first thing that I'm going to do is, normally each term in the denominator becomes its own fraction, where you'll go, so we have some fraction or some coefficient a divided by the first term plus b over the second term. But when I have a term squared, it gets a little bit different. Because if I were to really write every term out fully, this would be s minus 2 times s minus 2 times s minus 1, right? So the way that we account for when we have one term squared is first we have to have a over that term squared, so s minus 2 squared, plus b over s minus 2 to the first. Anytime you have a term squared, you have to do both of these. And then we have plus c over s minus 1, which is that last term that we have. And now, similar to how we did earlier today with undetermined coefficients, I now just need to find these values of a, b, and c. And it's good because I have a nice equation that I can use to find them. So, the first thing that I have to do in any partial fraction, once I set this up, is we want to get rid of denominators. We don't like fractions, we don't like denominators, let's get rid of it. So how do we get rid of denominators? Well, we're going to multiply the entire equation by this denominator right here. So I'm going to multiply everything times s minus 2 squared times s minus 1. So I'm going to multiply this term times s minus 2 squared times s minus 1. S minus 2 squared times s minus 1. S minus 2 squared times s minus 1. And when I multiply this left side by s minus 2 squared, s minus 1, we notice that the entire denominator goes away. When I multiply this term, I notice that I now have an s minus 2 squared in the numerator and denominator, so those go away. Here, one of the s minus 2's go away, so that becomes an exponent of 1, and that goes away. And the s minus 1 goes away. So now, rewriting that, I'm left with 5 is equal to a times s minus 1 plus b times s minus 2 plus c times s minus 2 squared. Yes, it would be. Thank you. It's b times s minus 2 times s minus 1. And then c times s minus 2 squared. So this is the equation that we're left with right now. And I'm trying to figure out what does a, b, and c equal. There's a couple different ways that you can go about this. I know some people will choose a value of s that makes a term go to 0 and then evaluate for the other constant. I think you can do that. I don't like to do that. I like to write it out basically the same way that you do with undetermined coefficients. So I like to first distribute these all out, and then from there I'll look at all my terms that have an s cubed, an s squared, an s, and then a constant. And then we'll figure it out from there. So that's how I'm going to do it. If you have a different method that works for you for solving from here, go for it. I'm going to do this method. Excuse me, this method, because I like it and it works for me. 5 is equal to as minus a, right? That's just distributing this right here, plus, I know that this s minus 2 times s minus 1 is going to be s squared is s squared minus 2s minus s, so minus 3s plus 2. So this whole thing is going to be times b, so I'm going to have plus b times s squared minus 3bs plus 2b. And then the s minus 2 squared term is just s squared minus 4s plus 4. So I'm going to have plus cs squared plus or minus 4cs plus 4c. So now I got a bunch of terms, and I have 3 unknowns. So now I can look at, first, I'll write down all of my s squared terms. On the left side, I have no s squareds. On the right side, I have b plus c. Then I look at all of my s to the first power terms. And on the left side, again, I still have 0. On the right side, I have a minus 3b. Should be negative a, thank you. No, it should be positive, because that's a positive as. Because we're looking at our s terms. So it's a minus 3b minus 4c. Then we look at all of our constant terms. On the left side, we have 5. On the right side, we have that negative a plus 2b plus 4c. I now have a system of equations. I have 3 equations and 3 unknowns, so I can solve it. So let's go through and solve it. I know that from the first equation, I get b is equal to negative c. I can plug that into the second equation, and I get 0 is equal to a plus 3c minus 4c. So I just plugged in that negative c for b. This tells me that I have a minus c is equal to 0, which means a is equal to c. And I can take both of those and plug them into this last equation. So I have 5 is equal to negative c minus 2c plus 4c. So I have 5 is equal to c, which means a is equal to 5, and it means that b is equal to negative 5. Now that I have all those, I can plug them into that partial fraction that I set up before. So I now know that, jumping back to this step, I said that y of s was equal to this is equal to all this. I'm going to say that y of s is equal to all this. So y of s is equal to a, which I know is positive 5, over s minus 2 squared, minus 5, because I know that b is a negative 5, over s minus 2, plus 5 over s minus 1. So now, even though we can't see it anymore, I have now finished that step of getting the right side to look like something that I can now take the inverse Laplace of. The last thing that we got to do, take that inverse Laplace, so that way we can get our final answer. So I know the inverse Laplace of capital Y of s is just capital Y, or is just y of t, which is the solution to my differential equation that we're trying to solve for. So if I take the inverse Laplace on the left side, I'll have y of t equal to something. When I take the inverse Laplace on the right side, I'm left with that something that is the answer to my problem that has already accounted for all of my initial conditions, my homogeneous, and my particular. So let's do that. When I take the inverse Laplace of this whole big thing, I get y of t is equal to, this first one's a little bit more tricky, so we'll start, you know what? No, they're all as equally difficult. We notice that we have this s minus 2 term, right? That it doesn't really fit any of these. We know that it looks pretty close to what I have right here. Actually, the only difference is it's squared. So if you remember from earlier in the problem, we had something similar when we turned something into a 1 over s minus a squared, because it's being multiplied by that t term. So this one, since we have that that's squared, it's going to fit this format, where I know that it's really this in disguise, just instead of s, I have an s minus a. So anytime you see an s minus a term, or s minus a constant term, always be thinking that it is this format, because notice how it's just the normal inverse Laplace, but everywhere that there's an s is normally an s minus a. So always look to that e to the at f of t term. So what that means is when I'm taking the inverse Laplace of this, I can imagine that this is just 5 over s squared. And then I'll account for that negative 2 by multiplying it by e to the at the end. So if this was just 5 over s squared, I know that I can bring the constant 5 out in front. I now have 1 over s squared, which just tells me that it's t to the first. Right? Because if I have 1 over s squared, that means my n is equal to 1, which means I have t to the first power. But now I have to account for the fact that it's not just s in the denominator, it's s minus 2, which tells me that a is equal to 2. So I know that a is equal to 2, I have e to the 2t. So this is the transform of this first term. I'm going to do the same thing with the second term, except now this is just pretend it's 5 over s, so it's just a constant. So I don't even have to worry about multiplying it. So I'm basically just in this e to the at term, where I have a constant over s minus a, which is exactly what we have right here. So we have minus 5, because I bring that constant coefficient out in front. So now it's 1 over s minus 2, which means it's just e to the 2t. And then this term, it's the same, very similar thing. We just have plus 5e to the 1t. And this right here is the answer to that differential equation we wrote down. Notice how we accounted for homogeneous in particular and all of our initial conditions. If you have any questions, come up, let me know. Fill out that form. That's my name and email.
I think maybe we should move this to the other